Okay, let's start. So I just want to do a couple more optimization problems, and then we can move on to anti-differentiation, which is kind of the precursor to integration, if you ever heard of that. Okay, so everyone see this question here? So we have a cylindrical can without a top, and it's made to contain some amount of liquid. So the question is to find the dimensions that will minimize the cost of the metal to make the can. Okay, so first of all, what is the volume? What is the volume of a cylinder? Anyone remember that formula? If you don't remember the formula, you can see it by the picture. So let me draw the picture, and I'll wait for an answer. Good, yeah, pi r squared times height. So, right, you have a pi r squared, that's the circle. And then you pretty much stack the circles up with some height. That's pi r squared times height. Okay, so we want to find the dimensions that minimize the cost of the metal to make a can. So what do we want to minimize? What formula or what about the cylinder do you want to minimize? If you want to minimize the cost of the metal. Like, what is the metal in the can? Like, how could you describe the metal? Surface area, right? Do you remember the surface area of a cylinder? No idea. We can figure it out. So what do you think the surface area is? Well, at least there's some pi r squared, right? Do you agree with that one? Plus stuff. So what's the stuff? It's all this on the outside, right? So it's that kind of like tube you want to we need to find the area of. So why don't we do this? Let's cut the cylinder with some scissors on the side here, and then let's open it up. If I open this up, what kind of shape do I get? So let's open up the. Let's pretend there's no. Let's pretend there's no bottom. So we just have like a cylinder with no top and bottom. If we cut a cylinder and then unravel it, what type of shape do you get? Do you have an idea? A rectangle, yeah. Uh, so this is what is this length? So all we need to know is that length and this length, right? Yeah, this one is h. Do you have an idea what this length is? Good, circumference. Right, when you unravel it, this becomes the length of your rectangle. So the circumference of the circle is 2 pi r. So that's it. The surface area is pi r squared. So technically, if it's closed, it's 2 pi r squared plus 2 pi r h. But in this question, we have without a top, so the surface area is pi r squared plus 2 pi r h. All right, is that okay? I don't know why the color disappeared, but okay, so what are we trying to do? We're trying to minimize the surface area, yeah? So what do we need to do to the surface area? How do we minimize surface area? From the derivative, right? So I want to show just one trick. It's not really needed here, but so notice in this problem here, you might want to solve for h. So one thing you could do is note that h is a function of r. H is a function of r. So one thing you could do is just, you don't have to substitute immediately. You could just use the product rule on RH. So just another kind of method you can do. It can be helpful for some harder problems. So what is it? It's the derivative is 2 pi r plus 2 pi, and then using the product rule on r times h, you get r h prime of r plus 1 h of r. So that is the derivative. So now on the side, you can solve for h and r, or so you can solve for h. So what is h of r? H of r is v over 2 pi r. And then h prime of r is what? How do you solve for h prime of r? Yeah, so you can use the quotient rule, but you don't always need the quotient rule. I always like to do these as a chain rule, like that. So what would it be in that case? Okay, we'll use the product rule, or the power rule. So it's negative v over 2 pi r to the negative 2. So negative v over 2 pi r squared. That's h prime. Okay, so now let's plug this in to our derivative. So we implicitly differentiated this. Okay, so you have 2 pi r plus 2 pi r times h prime plus h. That's v over 2 pi r. Okay, so let's simplify this a bit. So here's r, and here's another r. So so what happens? We get 2 pi r plus 2 pi negative v over 2 pi r plus v over 2 pi r. Okay, so that, let's see, does that make sense? Just 2 pi r? Okay. Wait, I think something happened here. Right? That shouldn't be right. Can someone check my work? Make a mistake somewhere? Oh, I see what happened. Right, so no one caught it. What is h? I wrote down h wrong. H is v over pi r squared. Right? So what is h prime? It's negative 2v over pi r cubed. So that does change things. Okay. Okay, so what we get is 8 as r negative 2v over pi r cubed plus v over pi r squared. Okay, so in that case, we get cancel, cancel. We get negative 2v over pi r squared plus v over pi r squared. All right, so now it's plus 2 pi negative v over pi r squared. Okay, so what do we do with the derivative? So now that we've found the derivative, what do we do with it? Set equal to 0, right? So we set this equal to 0. Notice that we get 2 pi r cubed minus 2v over r squared. So we have 2 pi r cubed minus v. So solving for r, we get r cubed is equal to pi r cubed minus v is equal to 0. And r cubed is equal to v over pi. And then r is equal to cube root of v over pi. Okay, any questions on that? Okay. So now that we found r, we need to find h to finish our problem. So what was h? Well, v was equal to pi r squared times h. So we just plug r in. And this is squared. Okay. So what is this? We get v is equal to pi, and then we have a cube root of v squared and a cube root of pi squared times h. Can someone tell me what pi over cube root of pi squared is? How do you simplify this? Well, so pi over cube root of pi squared is pi 1 minus 3/2, or other way around, 2/3. So it's pi to, what is that, 1/3? Okay, so we have v is equal to cube root of pi, and then cube root of v squared, and h. Okay, let's divide both sides by cube root of v squared. So we had done that, and it's cube root of v is equal to cube root of pi times h, and then dividing by cube root of pi, we get cube root of v over pi is equal to h. All right, those are the dimensions. So it's the same radius and height. And specifically, when it's cube root of v over pi. So whatever your volume is of a can with an open top, to find the dimensions that minimize the surface area, minimize the cost, you want the radius to be the cube root, or as close as possible to the cube root of v over pi. Okay, so let's do another one. Okay, so you have a piece of wire that is 10 meters long and is cut into 2 pieces. So let's first draw that. So we have a piece of wire that's 10 meters long, and you cut it into 2 pieces. So you don't know where you cut it. It doesn't say cut in half. It says cut. So maybe it's here. Maybe that's the cut. So let's denote the cuts by, let's do this one. The left one as the x, and the right one as y. What must be true about x and y? If you cut it into 2 pieces, and one of the pieces is x and one of the pieces is y, the sum must be 10. So immediately we have a constraint, is that x plus y is 10. So we have a constraint. Okay, so now let's read the rest of the question. One of the pieces is bent into a square. Okay, let's do the x. Let's make that one the square. Okay, so you bend x, you make a square, and one of this is bent into an equilateral triangle. So you bend y, and you make an equilateral triangle. Can someone tell me the sides of the square and the sides of the equilateral triangle? Good, yeah. So since in a square all the sides need to be the same, every side is 1/4 of x. Same is true for an equilateral triangle. All the sides need to be the same, so all sides is 1/3 y. Okay, so what we want to do is find the area of the square and the area of the triangle and determine what x and y must be so that the area enclosed is maximum or minimum. Okay, so what is the total area enclosed? So we want to agree with the, yeah, okay, let's see. Yeah, 1/16 x, we want x to be squared, right, when you multiply them. And then, so okay, let's first write this as, so the square area plus the triangle area. So yeah, so S of x, the square area, is right, that's 1/16 x squared. What about the triangle area? That's a little harder. We don't know how to find the height. Yeah, so let's talk about the height. That is right. So it's 1/2 base times height. So let's sketch it a little bigger. Here's 1/3 y, and here's 1/3 y. How do you find the height? So what is the height? This is the height, right? So one thing you can, okay, wait. Yeah, cut in half. So where are you cutting in half? You take the vertex here and you drop a perpendicular. You get 2 right triangles. Now the height of this triangle is the height of the whole equilateral triangle. All right, so how do you find that height? Yes, Pythagorean. So only thing we don't have is this length, right? But what is this length? To use Pythagorean? Yeah, it's 1/2. Yeah, whenever you cut an equilateral triangle on its vertex, it always cuts the base in half. So this is 1/6 y. Okay, so this means that the height squared plus 1/6 y squared is equal to 1/3 y squared. Okay, so what is that? H squared plus y squared over 36 is equal to y squared over 9. So if you clear the denominator by multiplying by 36, get 36h squared plus y squared is equal to 4y squared. Okay, you get 36 h squared is equal to 3y squared. Then you get h squared is equal to 3y squared over 36. And what is that? 12, right? Y squared over 12. So that means that h is equal to y over square root of 12, or y over 3 root, yeah, 2 root 3, or if you really want to do it, y root 3 over 6. Okay, so that is h. Okay, so any questions on finding h? Okay. Okay, so that means, so now what, using this now, what is the area of the triangle? It's 1/2 base, which is 1/3 y, times height, which is y root 3 over 6. Okay, so that is y squared root 3 over 36. Okay, any questions on that? Okay, so that is our t of y. So let's do a new page. We have area is equal to the square of x, or the area of the square in terms of x, and the area of the triangle with expressions in y. So our x was 1/16 x squared, and our triangle was square root of 3y squared over 36. Okay, so how do we take the derivative? Look at our constraint, right? Constraint was x plus y is equal to 10. Okay, so what do you want to solve for, x or y? I think solving for x might be easier because this is a bit more of a complicated term. So maybe the thing you want to make more complicated, put it on the easier term. Okay, so what is this? X is equal to 10 minus y. So what do we get? 16th and then 100 minus 20y plus y squared. And then, okay. So that's our derivative. Oh, sorry, that's just a. A of y, not a of x. So we haven't found the derivative yet. Okay. So let's find the derivative now. So notice I don't really need to simplify it to find the derivative, right? So what is the derivative is 1/16 times 0 minus 20 plus 2y, and then plus 2 root 3 over 36y. Let's see, what's 2 divided by 36? Is that 18? So we get 1 over 16 negative 20 plus 2y plus root 3 over 18 y, and this is equal to a prime. Okay, so we want to set the derivative equal to 0, right? So we have 0 is equal to all this. To simplify a little bit, take out a 2 there. So we have 1/8 y minus 10 plus root 3 over 18 y. So we have 1/8 y plus root 3 over 18 y minus 5/4 is equal to 0. So we have 5/4 is equal to 1/8 plus root 13 over 18 y, and then so whatever that is, let's see. Uh, 18 plus 8 root 3 over 8 times 18. So it's 8 times 18 over 18 plus 8 root 3. 5/4 is equal to y. You can simplify that a bit. 2. So we get 18 times 5 over 9 plus 4 root 3 is equal to y. Okay, so barring any computational errors, that's y. Can someone tell me if this is a max or a min? So look at the derivative and say why you think it's a max or a min. All right, so yeah, so this is the derivative. So it has a positive slope. So it goes from minus to plus. So it's actually a min. Right, the slope is positive. Of the derivative, the derivative is a line. Okay, so then what would x be? X plus y is equal to 10. So then solve for x. So one thing we do have to worry about for this question, though, is that there are other possibilities that could happen for our cuts. We could just not cut. So what would it mean to not cut? Does that mean we only have 1/4 x, or what was it, 1/16 x squared? Or so what was the other one? Y squared root 3 over 36, or y squared root 3 over 36. So we just plug the whole thing in for y and x respectively. So what you want to do is, so this calculates for an area when you do the derivative way. So you want to compare these three values. And we're essentially using extreme value theorem here. Right, there's a max and a min to what x can be, right? What is x can't be larger than 10, right? And that wouldn't make sense. And x can't be smaller than 0, because that would also not make sense. So so there is a upper and lower bound. So that implies that extreme value theorem can be used. So comparing all these three values, the smallest of the value would be the minimum, and the largest of the values would be the maximum. Okay, so by the way, I did post in the general chat a PDF of 3 questions that might be on the homework. One of them was about a kite. One of them was about surface area of a cone, and one of them was about some cost function. So if you're stuck on those questions, you can look at those solutions. But we're going to move on from optimization now to antiderivatives. Okay, so what is an antiderivative? So let's start with this just kind of true fact, and we'll prove it. If f and g are differentiable functions, and f prime is equal to g prime, what do you know about f and g, you think? In a sense, they're parallel. So there's some notion of, well, okay, what do you mean by parallel? Parallel really only means for lines. So how do you mean parallel? Okay, yeah, actually, if these were lines, if f and g were lines, they'd be parallel. Yeah, same slope. So yeah, so let's do the example for lines. If y is equal to mx plus b is a line, what is another line that has the same derivative? Give an example. We'll jump off on parallel, and we'll talk about that. If f of x equals mx plus b, find another function such that f prime is equal to g prime. Can you think of one? Just any random. Sure, just mx, that works. Mx has the same derivative. Right, what is the shared derivative? M, yeah. So yes, and these are parallel, right? These are parallel lines. Right, mx runs to the origin, and then mx plus b has the same slope, but does not run through the origin. So they're parallel. Okay, so there is some notion of parallelism when two functions have the same derivative. So let's think more about let's think of some other functions that have the same derivative. Can you think of, let's start with x squared. Can you think of a function that has the same derivative as x squared? First of all, what's the derivative? Two x. Yeah, so what is a function that has the same derivative? X squared plus 80, I like it. X squared plus 80. That has the same derivative. So let's sketch these two things and see, let's understand maybe what's parallel. Let's pretend this is 80. Okay, what's another function that has the same derivative? Was 80 special? What what's another example? 40, yeah, that's another good one. So that could be like down here. What's the same about all of these lines? Or these parabolas? What do you mean the same? Good, yeah, they're displaced. So these are vertical translates. That's what you mean by displaced. How do you describe any type of vertical translation? Like if f of x is a function, what is a vertical translate? A vertical translate of f is what? F prime is the derivative. So, like, what I mean, so if this is f of x here, what brings you up here? Like, what do you do to f to bring you up to this one? You add 40. So, if you do any sort of vertical translation, you always do, you add a constant. So in that case, it's plus 40. If you wanted to go up here, it'd be plus 80. If you want to go down here, it'd be like x squared maybe minus 1. You'd plus negative 1. So does that make sense? So all functions, we don't know right now. It could be more than just f of x plus c, but at least all functions with the derivative of f, at least a lot of them are of the form f of x plus c. So the claim is that all functions that have equal derivative are just vertical translates. That's the claim. If you have two functions with the same derivative, then f is a vertical translate of g. Okay, so any questions on that? Okay. So let's think about it. So we want to show f prime of x equals g prime of x implies f of g is equal to g of x plus c. So another equivalent statement is to say that the difference is equal to c. So we're going to play on that. So let's look at f. So if f prime of a is equal to g prime of a for all a, let's see what the definition of the derivative tells us. With the limit as x approaches a of f of x minus f of a over x minus a is equal to the limit as x approaches a of g of x minus g of a. So let's subtract both sides. So the difference in these limits is 0. So let's just combine the fractions. It's good practice for final. So the same denominator, so we can just combine. Now, can someone tell me how you can, or I can just do it. It's not very obvious. So let's combine the x terms and the a terms. Let's see what we get. We get f of x minus g of x over here, and then minus, and then I'll put in parentheses, f of a minus g of a. Okay, what is this? What is that? Looks familiar. Let me write it a little bit differently. Does that look more familiar? Yes, that is a formal def. So it's the same one as up here, right? This is the same thing as f prime of a equals g prime of a. So yeah, this is the same thing as f minus g prime of a is equal to 0. Yeah, this is all f minus g prime. Okay, so if this is true for all a, that means that f minus g prime of x is equal to 0. Huh. What's it? So you have a function whose derivative is 0 everywhere. What kind of function is that? What type of function has derivative 0 everywhere? Constant. Yeah, there's only one only one continuous differentiable function that's just 0 everywhere. That's the constant function. So that means that f of x is equal to g of x plus c. Okay, so this is pretty much the fundamentals of antiderivatives. And so let's define that antiderivative. So if f of x is a continuous differentiable function, big F of x is called the antiderivative. Where big F prime of x is equal to f of x, and f of x consists of an infinite set of functions of the form g of x plus c, where g prime of x is equal to f of x. So the antiderivative is a lot of things. So in layman's terms, you can say antiderivative is functions, the set of functions whose derivative is f. Okay, any questions on that definition? So the antiderivative is not a single function, but it's an infinite amount of functions, because there are so many functions whose derivative is f, because you can add anything you want. Let's take those parabola examples, right? Here, we found 3 examples of functions that have the same derivative. So let's just do an example to get us started. Let's do the antiderivative of a constant. Okay, what's the antiderivative of f of x equals a? So again, it's what are all functions whose derivative is a? What types of functions have constant derivatives that you know of? Think about all the derivatives that you do, and when you take the derivative, you get a constant. Yeah, variables when the power is 1. So what are those things called? So maybe I'll give this a different letter. Yeah, all linear functions. So what must be true about the linear functions? What must be the same between all of them? So you have y equals x plus something. What goes where? So not all linear functions in the world, right? Yeah, only the ones that have mx. And anything here? Does what needs to be over here? What can be over there? Yeah, any constant. Right? So that's the antiderivative. Okay, so let's do another one. What is the antiderivative for cosine? So all functions whose derivative is cosine. Right. So this is kind of the trick with antiderivatives. If you know one function whose derivative is cosine, then you know all of them. So that's kind of the tip here. If you know one function whose derivative is cosine, then you know all of them. So that's it. Yeah, big F of x is equal to sine of x plus c. And then if you don't believe, big F prime is equal to cosine, which is equal to f. Okay, so let's do one more, and then we'll take a break. How about x squared? Oh, we haven't done x yet. What about x? So all functions whose derivative is x. So one thing I like to do is, if you don't know it right away, we'll talk about like what must be true about the function, the antiderivative. So what do you think must be true? Think about your derivative rules. What form should the function have to make a derivative as x? Like, at the very least, what should it be? Yeah, it has to be some power of 2. So let's just test it. What happens if it is x squared? What does that give you? 2x. So, but that's not correct, right? Because we just want x, but we have 2x here. So how do you compensate for the 2x? So if the derivative of x squared is 2x, yeah, if we just divide by 2, we get x. So you found the antiderivative. It's x squared over 2, then plus c. Any questions on that? Okay, so let's take like a 5-minute break, and you tell me what the antiderivative of this is, and then also tell me for what n does this is this not true? Is the formula not true. So you can make a formula for all n except for one. Only one n doesn't work with this method. Okay, so let's meet back at 8:37 and you can work on that. Does the question make sense, by the way? All right, hope it does. Let's meet back at 8:37.